Institution, Christmas Lectures, Lecture 3, Muscle Power. 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3.
I expect you've all been doing a lot of washing up lately. Have you ever stopped to wonder how soap or detergent works? Soap and detergent molecules are rather like this. It's a simple model. This end of the molecule likes to be in water. It's a polar molecule, like water itself. But this end of the molecule likes to be in grease. It's an oily molecule, like the compounds of carbon and hydrogen that we looked at. So if you put a soap molecule in water, it sits in the water so that the water-loving end is down in the water and the greasy end is elsewhere looking for something to stick into. Well, if you put soap or detergent then onto a grease spot or greasy plates or something, the greasy end of the molecule sticks into the grease spot and the water-loving ends stick out all round it, and that makes the grease spot soluble in water and the water can carry it away. It goes back to this problem of oil and water mixing. Here again is some oil and water which separate out to form two layers. If I shake this up, then, as you know, it looks as though it's mixed up to begin with, but in fact it hasn't mixed up very well. They won't mix, they'll separate out again. But if I take the same sort of oil-water mixture, and this time I put some detergent in, like this, and then I shake it up, the detergent really will help the oil and water to mix. So now we get this emulsion, little drops of detergent, little drops of oil rather, covered with detergent molecules which are making them soluble in the water. So that won't separate out into two layers, although left to themselves, the oil and water do separate out as these have already begun to do. So that's how soap works. Why have I said all that? Because the enzyme molecule we were talking about last time, lysozyme, which is here, this molecule, in one way is a large soap molecule. It's arranged so that the components, which are polar, which like to be in water, all come on the outside. So they're painted blue here. These blue chains sticking out of the molecule are water-loving components. They like to be out in the water. And the greasy components, they're painted yellow here, and the middle of the molecule is made of these greasy components. So it's behaved as a soap would. It's pointing the water-loving ends outwards and keeping the grease inside. Ah, but you can say to me, we know that the protein chain, which carries all these side chains, if we go back to this old model, this protein chain is made up of links which are themselves water-loving. They carry a little positive and negative charges. They like to be in water. What's happening to them? Well, they're painted red in this model, and you can see that sometimes they're on the outside here, but also they go through the middle of the molecule. How is that arranged? Well, the protein chain is coiled up in two different ways when it goes through the middle of the molecule. It's partly coiled up to form this spring-like structure that we found when we were thinking about hair, in which the positive and negative pieces point at one another. So in this structure, these positive and negative charges are quite happy cancelling one another out, and they don't mind whether they're in water or not. They're looking after themselves. So in this big molecule, there are little pieces looking like little bits of hair. And in another way, they can fold up, as we found in silk, now with the chains stretched out in long lines, but again, parallel to one another, so that the positive pieces are looking at the negative pieces and taking care of one another. So again, this structure doesn't mind whether it's in water or not. The charges are taking care of one another. So if we look at this big molecule in slightly more rough detail in this model, we are looking only at the way in which the protein chain itself is arranged. And the green part here, the color part painted green, that's like silk. This is arranged like the protein chain in silk, with these positive and negative charges taking care of one another. And the parts painted yellow, they're arranged like the protein in hair, and again, with the positive and negative parts taking care of one another. So they don't mind whether they're in water or not. For the rest of it, it takes up this very particular shape, which depends, you'll remember, on the chemical structure, on the order in which these components are arranged. This particular order of components leads to that shape. And what happens is that as soon as the long protein chain comes into contact with water, it automatically takes that shape, just as soap molecules, when we put them into water, automatically line up in the right way. So we have here a big soap molecule. But what about the way in which this brings about a chemical reaction? This molecule, you'll recall, breaks a chemical bond in the wall of a bacterium. So we can go back to looking at that. Here is a model in which a part of that bacterial cell wall has been built in to the enzyme. Here the enzyme, lysozyme, has a groove in it into which this part of the bacterial cell wall exactly fits. There are 6 sugar rings fitting there. And somehow the enzyme brings about the breaking of a chemical bond between the 4th and 5th sugar ring. Well, it's all very well to have this 3-dimensional jigsaw puzzle fit, but how does the enzyme make that bond break? Well, to think about that, we have to think a little bit more about chemistry. So let's go back to our water molecules. You'll remember that water is made of oxygen connected to 2 hydrogen atoms. And the connections, the chemical bonds, each involve 2 electrons. There is 1 electron coming from the hydrogen and 1 electron coming from the oxygen, and together they form a chemical bond between the hydrogen and oxygen for each of these 2 hydrogens. Now, these molecules stick together, you'll remember, because there are little positive charges on these hydrogens and a few electrons seem to congregate down here to give it a negative charge, a partial negative charge. Now, there's another way in which these molecules can come to pieces. Here's another one. Suppose that the nucleus of this hydrogen atom, hydrogen has a nucleus with 1 positive charge on it and 1 electron. Suppose the nucleus gets away by itself. If it got away by itself, it would come away from this molecule and it would have a positive charge. So here it is, it's got away with a positive charge. But it's left its electron behind. So what's left of the water molecule, it has now a negative charge. So let's give that a negative charge. What's happened is that the water has broken into these two pieces, this part carrying a negative charge, and the proton, the nucleus of the hydrogen atom, has got away with a positive charge. Now that happens to numbers of chemical groups when you put them in water. And when you put such a compound in water and it loses a proton like that, we call that an acid. And the more easily it loses the proton, the more acidic it is. Now, some of these groups on an enzyme, these components, are acids. And here's a model of one of them. This little model shows, if I cover up the protein chain part of this component and just show you the side chain, it has a carbon atom attached to these two hydrogens, and then another carbon atom attached to one oxygen over here with one of those double bonds we talked of, and attached to another oxygen here, which is itself connected to a hydrogen. So this part looks a bit like water. And if we lose this proton now, so that falls off and goes into solution, what is left is carrying a negative charge. And the negative charge would be, as I've drawn it, on this oxygen atom. Now this is really quite a familiar little substance, the one that we've got in this side chain. That's an acid which makes vinegar acid. Ethanoic or acetic acid, it's called, and that's what makes vinegar acid. Now, there's another sort of component in these proteins, and that has the opposite effect, that it likes to collect protons, hydrogen atom nuclei carrying a positive charge. Let's go back now to nitrogen. We didn't think about nitrogen earlier on. Nitrogen has 7 electrons altogether, whereas carbon, you'll remember, has 6 and oxygen has 8, so that's in between the two. And nitrogen likes to make 3 chemical bonds. So here it is making bonds to 3 hydrogen atoms. That's a molecule of ammonia. But this nitrogen has 2 electrons located about here, which are looking after one another, but they wouldn't mind interacting with a proton. So if a proton comes along to stick on there, let me find a proton that will stick on there. The 2 electrons here will arrange to form a chemical bond, and the proton sticks on, and we've now got something that looks much more like a carbon atom with 3 hydrogens, but it's now carrying a positive charge. That is, it's like to pick up a proton, and it's carrying a positive charge. So there are some compounds among the protein components here which have this property. They like to collect protons and take up positive charges. Let's have a look at a little experiment about that. There are substances, and litmus is a very well-known one, litmus, which change color according to the acidity of the solution. If you put an acid in, it's one color. That is, if you put a lot of positively charged protons in, it's one color. And if you take them away again, it's another color. Now here's an indicator, and here is some ammonia. Yes. If I put in a spot or 2 of this, you see that the indicator turns a nice red color. That's picking up all the protons that were about there. If I put some vinegar in, on the other hand, from this, then that color will disappear again. There it goes. There's the colour disappearing. If I shake it up, it'll go all together. And I can keep on doing that if I'm lucky. If I put some ammonia back in again, then it will take more this time because we had some acid in. I'm afraid I put in too much acid, so it didn't work again. But never mind, that's acids releasing protons being left with a negative charge, and the opposite, ammonia-like molecules, picking up protons and acquiring positive charges. Now, how is that going to help us with understanding how enzymes work? Well, now we have to go on and think a bit more about a chemical reaction. So let's look at this model to illustrate a rather simple chemical reaction. Here we have yet another model, this time of a carbon atom in the middle, connected to 3 hydrogen atoms and some other atom over on this side. And here, approaching this molecule, we have an oxygen carrying a negative charge. Let's suppose that that comes from one of these acids I've been talking about that was left with a negative charge. It's also carrying with it the 2 electrons, that is, that are needed to make a chemical bond. Now, if this group approaches the carbon here, a number of things happen. As it comes closer, it begins to interact with this carbon atom, trying to make a chemical bond with it. And that begins to weaken the bond on this side, and the bond over here itself begins to stretch, and the atom here begins to pick up a negative charge also. And we push on, getting harder and harder, until in the middle there you will see these are about the same distance from the central carbon atom, and the arrangement of the hydrogens now has changed, and this carbon in the middle by now will have picked up a positive charge because it's lost most of its share in these electrons without picking up a share in these. Then I can push on, and now finally we've made a bond with this group over here, and we've lost the connection with this one. Now, that's a rather simple outline of one sort of chemical reaction, and it could go the other way. If this atom approaches, then we go back again through that point, and this one goes away. It's all rather like pushing a rolling stone over a hill. You push and push up here, and it gets harder until in the middle here, you're at the top of the hill. And then the reaction can go, or the stone can fall down the other side, or it can go back the way it came and push you back down the hill again. The difficult place to get to in this chemical reaction is in the middle there, where we have a negative charge on this one, a negative charge on this, and a positive charge here. What the enzyme must do is try to reduce the size of this hill. It must somehow favor the formation of this structure, the one in between the position it started from and the position it's going to end. That's what the enzyme must try to do. And if it can do that, it will make it easier to push the stone over the hill, that is, for the chemical reaction to go. Now, with that amount of explanation, let's see if we can at all understand how lysozyme carries out its chemical reaction. And we'll try to do that with some drawings here. That's a drawing of the enzyme as it starts. Here's the enzyme structure. Here's the groove where the part of the bacteria fit. Over on this side, we've got a vinegar-like molecule, one of these acids. So it's carrying, because of the position it's in the enzyme, this one is carrying a negative charge on the oxygen. Over here is another vinegar-like molecule, and this time, because of the position it's in, it's holding on to its proton, so it isn't carrying a negative charge. Now, along comes the bacteria, and some sugars fit into this groove, and if I take that drawing away, in the next drawing, there they are, the sugars fitting into this groove, one here with a carbon atom connected to an oxygen atom, connected to a carbon of the next sugar, and there's the next sugar going on, and so on. Now notice that this carbon atom is up against the negatively charged oxygen over here, just like the atoms in the model I was showing you. And that will have the effect of beginning to weaken this chemical bond between the carbon and the oxygen, so these bonding electrons will be thinking of going away to do something else. This oxygen is developing a negative charge, so it's beginning to attract the proton that is over here. And it means that the bonding electrons holding that proton to this oxygen, they're thinking of going somewhere else. They're thinking of just leaving that oxygen negatively charged. Well, if all of that happens, we go on to the next picture. And it has happened, and we are left with the oxygen interacting now with this carbon atom, which has now got a positive charge. The bonding electrons have come around to this side and have stolen the proton from this oxygen. So this oxygen here in the sugar is now attached to a proton, to a hydrogen atom. And the bonding electrons from there are now over here charging the oxygen negatively. Well, now this part of the sugar, of the bacterial wall at the bottom there, that's now quite stable, and it can fall off. So it does that. Off goes half of that, and we are left now with this structure, with the oxygen on this vinegar-like molecule here interacting with the carbon, which has got a positive charge. And this oxygen over here is now negatively charged. But it's no use leaving it like that. This is really almost at the top of the hill. The enzyme shape was such that it brings about this structure. But where do we go from there? Well, water comes along. Here's a water molecule appearing and approaching this region. And if we look on at the next stage, water has come along and put its oxygen near to this positively charged carbon atom, and it's pointing a hydrogen across at this negatively charged oxygen atom. Now, the electrons in that bond, they are now wondering where else they might go. So they move round to form a bond here between carbon and oxygen, letting go of this proton. And these electrons come around to form a bond between this oxygen and that hydrogen. So let's see that happen. There we go. Now we have a bond from the carbon to the oxygen from the water, which has got another hydrogen on it, of course, and the other hydrogen has gone across and neutralized the charge on this oxygen. And now this piece can fall off. And when it does that, we shall find that the enzyme is in just the state it was in to begin with, like that, with this one negatively charged and this oxygen carrying a hydrogen. And that's a true catalyst, because at the end of all that complicated story of electrons moving around and charges, there's a hole in the bacterial cell wall, but the enzyme is just the way it was to begin with. Now that's an illustration of the sort of chemical reactions that are going on all the time in our bodies, and in chickens' bodies for that matter, doing all the things that have to be done for us to keep on living. For example, if we want to have energy and build new molecules and so on, we eat, and the food we eat has energy in it, which we need to use. So let's have a look at how much energy there is. Bill here has something left over from Christmas, some nice sponge cake. So let's see that that really is sponge cake. It is. You just eat the sponge cake. That'll be fine. Yes. Now, what we're going to do is to burn some of this sponge cake in a good... You want my sponge cake?
Well, There is no cheating then.
Right? Well, Bill is going to dip this into liquid oxygen. Here's the liquid oxygen. That's just to get a good supply of oxygen, which is obviously important in these reactions. When he's got it well soaked, and you can see the liquid oxygen boiling there and water condensing around it, he'll hang it over there, and then we'll see how much energy there is involved in that sponge cake. Well, you see, there's quite a lot of energy. Of course, it doesn't happen quite like that in your stomachs, perhaps. But what happens in your bodies is that the sugar in the sponge cake is broken down slowly and deliberately through a series of chemical reactions of the sort that I was showing to you. And in the process, which involves about 30 different enzymes, the body is making a new chemical substance. Now, this is a chemical substance which acts as a sort of fuel, in a sense as a store of energy in a way that I'll try to explain. It's rather a valuable chemical, but it's a straightforward white powder chemical, which you can see in this bottle. And it's known as ATP for short. I won't burden you with the full name. Now, this substance acts in such a way that when it comes into contact with water, a reaction takes place which liberates energy, which can then be used either to drive other chemical reactions or to provide mechanical work, and so on. So this is the intermediary, the key substance, which the body makes using the energy it gets from your Christmas dinners and so on. Let's try to illustrate that. Here's a beaker of water. It's fairly cold water. Would you like to come and help me with this experiment? Yes, that's fine. Just come out and what I'd like you to assure everybody is that this water's reasonably cold, so hold on to the beaker like that, and that's reasonably cool, isn't it? And if we look at this in the thermometer, I think we should just about see that it's about 20 degrees there, about 20 degrees. Now, here's a substance. It isn't ATP, because that would be too expensive, but it works in something like the same way. If you tip that into the beaker, and I'll stir it up, we'll see what happens. Right? Just tip it in. Jolly good. And I'll stir it up. Now, you hold on to the beaker for me around the outside. Is it getting warm? It really is. It really is warm. And if I measure the temperature, I can even see it steaming, can't you? If I measure the temperature there, then that really has gone up high. Can you see that? Looks to me like about 60 degrees. That really did get hot. Thank you very much indeed. So we see that this material that the body makes, when it interacts with water, it can release energy. There the energy was being just released as heat and rather wasted. But we want to use it to do mechanical work and so on. So now we're going to think about how that's done, and in particular about how muscle works. And here I shall need some help again. Melanie, I wonder, can you come and help me and show off your muscles? Very good. Let's move that back. Now, when Melanie wants to bend her elbow in this way, there's a muscle up here which contracts, it shortens, and it's held by a tendon onto the forearm down here. So when she bends that, you can see the muscles shorten and get thicker. That's tension from this muscle. Now, suppose she wants to straighten her arm out again. There has to be another muscle. This muscle relaxes, and there's another muscle underneath here, and that pulls down on this part of the arm, pulling the arm out straight again. So to bend it, this one contracts. To stretch it out again, this one contracts. Muscles come in pairs, working in that way. One pulling and the other letting go, then the other pulling and the first one letting go. Now, we're going to be talking about birds, turkeys and things. Suppose that Melanie were a bird. Then she would have somewhat different muscles. She would need to have muscles to flap the arm up and down. So birds have a muscle which is attached down here at the bottom of the rib cage and comes across to here, and that pulls down. That's a nice big muscle to pull down. Then there's another muscle also attached around here, which is really very clever in birds. It comes up here and over the shoulder blade working as a pulley, so that it's attached over here, and this then pulls up. So using these two muscles, wings can be flapped. Thanks very much, Melanie. Now, a turkey, as you'll know, has very big muscles of this sort. If you carve it carefully, you can see these two muscles in the turkey breast, but of course it doesn't fly very much. Let's have a bird that uses these flight muscles really very elegantly. And this is shown on a film made by Oxford Scientific Instruments of a hummingbird. Now this has been slowed down so that you can see the wings beating. And you see there that it can hover just away from the flower, dip in to pick up some food, holding its head very still with this elegant movement of the wings. Then, when it's finished with this, it can back off again and have another look, and then come into another flower, flapping its wings all the time, very elegantly. And then when it's finished all that, away it goes. Now, if we want to fly, it's more difficult. And here you see in this film the very dramatically successful attempt this year of a man to fly in this aeroplane called the Albatross. Has fixed wings, of course, but see how wide they are. And inside there is a man who is actually driving the propeller by pedaling. And in this device, he managed to pedal all the way across the channel, using really tremendous muscle power. Now, that tells us, I think, at least two things about flying, and it reminds me a bit of Christmas decorations. Can we have a look at the Christmas angel down there, please? Here's a typical sort of Christmas angel, but there are difficulties with it. As we've just seen, if that were made like us, then it would be a bit difficult to fly with little wings like that. So let's extend the wings, Bill. It will need bigger wings than this. And if it's going to have big wings like that, it will certainly need to have a quite sizable muscle on the front to flap them with. So the usual proportions of these Christmas decorations are not right if they are really to represent a creature that flies. Well, thank you very much. Cool. What we need now to think about then is, how does muscle really work? If we look at this model of an arm, this is like Melanie's arm. As the arm is stretched out like that, this muscle is stretched and is waiting to pull this up. And if we arrange some mechanism for let go, we can see if it can throw a ball over there. Not very well. Now this muscle is elastic. Do you think real muscle is anything like elastic? It was thought for a long time that it was so. So let's look at a model to see how elastic works. So far, we've been talking about molecules as though they were quite still all the time, not moving. But here is a chain. This is now representing a molecule which is still at the moment. But what we are going to do is put it into motion. As Bill turns the handle and it comes into motion, you see it contracts with these atoms whizzing around. And if I pull at this end and let go, you see that that's elastic. Thanks very much, Bill. Well, I suppose muscle might be a little bit like that, but it doesn't seem really very reasonable. Let's look at something which is more familiar biologically. What happens with collagen? Well, collagen does something strange when you increase the temperature just a little bit. Here's some collagen held at about 58 degrees centigrade, and you can see that there are long strands of it hanging down inside the beaker. If now we change the temperature of this collagen over not a very wide range, if we put this into water 10 degrees or so hotter than the original water, let's see what happens. And you see that that shrinks enormously. What's happened there is that the very regular structure of collagen that you saw earlier has got broken up. The molecules have started whizzing around as they were in the model of rubber, and the collagen molecules have shortened. Well, I suppose it's possible to think that muscle behaves somehow like that. But the trouble with that last one is that if you put the collagen back into cooler water, it doesn't stretch again. What we've seen is a reaction which doesn't go back the other way, like the reaction you get when you boil an egg and the protein in the egg white changes, but you can't put it in the deep freeze and have it go back to be an ordinary egg again. So we want something which will go both ways for muscle. And it all depends on looking in some detail at the actual structure of muscle. How are the molecules in it arranged in space? Well, here we have an experiment which Patricia can do for us, where we have a little muscle fiber in a laser beam. And if we put down the lights, we can see something really very dramatic. Here is the laser beam which goes straight through the muscle, scattered a little bit up and down. But on either side here, there are other streaks, and there's even a very weak one over here, a second one after that. 1, 2 on this side, 1, and a very faint one over on the other side again. So muscle is behaving rather like that pattern of lines drawn on a glass plate that we looked at earlier. So if we took the muscle away and put that pattern of lines in again, here's the central laser beam, and here are the beams on either side, which arise from the pattern of lines. Thank you very much indeed. So that tells us there's something about muscle which is rather like that pattern of lines drawn on glass. And it also tells us that that something means that the separation of the lines in the muscle is about the same as the lines on the glass that Patricia was using. That is about 3,000 lines in every centimetre. Well, let's have a look at that over here. Here is a drawing which shows what you see in a microscope when you look, a quite powerful microscope, when you look at muscle. Here are these lines, about 3,000 of them in every centimetre. So this is banded, striated muscle, muscle with these bands in it, which are running up and down as you look at this, and the length of the muscle is running from side to side. How can we understand how muscle contracts from that? Well, in the early 1950s, it became possible to look at muscle in a different sort of microscope, an electron microscope. And when you do that, then you see a rather more detailed pattern like this. Now these bands we are seeing in rather more detail. Let's concentrate on these. This is a dark band that you saw before, but now you can see that there's a repeating pattern here, we start from that thin line, we go through thick lines here, another line in the middle, thick line there, another line in the middle, and then there's another line like the first one, and then there's another repeating unit like that over on the other side. And this pattern repeats throughout the muscle. Let's have a look in the next diagram just at that rectangular piece of it. Here's a picture of that. Here's the first line we started with. Now, if you look horizontally from there, there are very faint traces of lines going horizontally across there, which then come to this darker band. If we go to the center, there are traces of thicker lines coming horizontally out of the center and coming also into this darker band, and in this band they overlap. If we look now at right angles, cut a section through the muscle this way, then we see the pattern down below. Let's move to this one first. We cut a section just through the thick bands coming from the center. Then you see, looking at the ends of these lines, which we shall begin to call filaments, looking at the ends of these lines, they're packed together in a nice regular way. Over here, the thin ones are rather irregular, but they come together in the middle to form a regular pattern with the ends of the thin lines, thin filaments, coming between the thick filaments in this regular way. Now, these things were looked at first in the early 50s by Hugh Huxley and Jean Hansen, and they, from this evidence, and Andrew Huxley and his colleagues from other evidence, suggested what this might mean, and I've got a model here that shows that. Here is the model. Here's the center line with thick lines, thick filaments coming out of it. And here is the line at the edge with the thin filaments coming out of it. Now the idea is, if this is a unit of muscle and you want to contract it, what must happen is that these thin filaments move inwards further and further into the thick filaments. So it contracts. This is called an interdigitating model, as though the fingers from two hands come into one another like that. The thin filaments in one way coming into the thick filaments from another. Then they might come apart again, relaxing for the next contraction, and then pull in again for the next contraction like this. Now that's all very well, but what is it connecting these filaments? Why should they pull into one another in that way? To understand that, we have to understand what these filaments are made of, and the slide over here shows us one of these. Here we have a picture of the thin filaments, and it's again an electron microscope picture taken by Hugh Huxley, and if you look at this little bit of it in particular, you can pick out a sort of wave going round like that, mixed up with another wave going round like that. Now it's known that the protein from which the thin filaments are made, it's called actin, is a molecule a bit like lysozyme, a nice spherical sort of molecule. But these spherical molecules come together, and they do it automatically by fitting together the greasy pieces and leaving the water-loving pieces on the outside to form long chains. And here are two long chains, and they are colored white and orange just to distinguish them. But they're not aggregated just in long chains like that. These chains have to twist together, so I'll see if I can twist these together. And then you ought to see a picture rather like the picture taken by the electron microscope of these two actin chains twisted together to form the thin filaments. What about the thick filaments? Well, let's see if we can see on the magnetic board what that's like. the thick filaments are made of molecules of myosin, where this part, the straight part, is arranged rather like the protein in hair, that long springy structure. But again, it has a blob on this end, which is an enzyme molecule, a more spherical enzyme molecule. Now these can come together, myosin molecules fit together, rather the way in which collagen molecules fitted together, to form long filaments like this, in which the myosin is pointing in two different ways. I don't have to build very much of this, I think, for you to show the idea. So we're building up here a thick filament, where this would be the center line, and there's a filament going that way and a thick one coming this way. And these globular heads, these spherical parts, form bridges between the thick filament and the thin filament near to it. Now, if we have a bridge from the thick filament to the thin filament, we can see whether that will help us to pull the two together. And here we have a graphic, and we'll see whether we can see that. Here, in this diagram, I've shown the thin filament along the bottom as a row of circles, and the thick filament up here as a horizontal bar, and here are the cross bridges. And you can see at the moment they are arranged so that this one is at an angle like that, making a connection with actin, the thin filament. The next one is at a different angle, like that. So the shape of these two has changed, is different. And this one isn't making any contact with the thin filament at all. Well, now suppose that this one could change to that shape. It would pull the thin filament along in that direction. If you go on to the next graphic, let's see if that will happen. There we are. It's moved along to the next shape. Meanwhile, this one has come off. Well, you can't see that, can you, on the monitor? One has come off and the other has attached. Now, if we go on to the next graphic, the one that's at the right angle will switch to the next, and the actin should move along again. There we are, like that. And if we run these together like that, then you see that the thin filament, pushed along by these cross bridges, should be moving along. All right? Now, it's all very well to give you that in outline, and that's essentially the model proposed by Hugh Huxley, but we need to know a great deal more detail about it. And in order to do that, we should have to be able to look at these molecules in the same sort of detail that we've been looking at lysozyme. What we do know is that every time the shape of the cross bridge changes, one molecule of ATP is used up. So that's, in principle, how it works, and we shall have to wait a little while, I fear, before we can see in the same sort of atomic detail exactly how muscle does work. But still, muscle is something that we know about mainly as meat, because we eat it. So let's think about muscle now as meat. Why is meat sometimes tender and sometimes tough, and so on? Well, let's come back to this model. If I put this into the extended shape, when we chew on meat, the muscle breaks most easily at these places where there are only the thin filaments. So that if the meat is treated before you eat it, at whatever stage, in such a way that it's all contracted, if I now let this contract, then it's more difficult for it to break in these regions, and the meat tastes tougher. That means the way in which the meat is prepared over all of those stages is very important in deciding whether the meat is going to be tough or not. We really want it to be so that the muscle is extended. But then again, of course, this is an engine made of protein, as I've been saying. If we could do something which would help break down the protein before we begin to eat it, then it would be easier to chew. And there are enzymes, and of course you have them in your digestive systems, which break down protein in this way. So if you add some of those enzymes to the meat, it would make it more tender. Well, you'll know it's possible to get substances called tenderizers, but you also sometimes, if you're good cooks, do this in a different way. If you eat gammon with a large piece of pineapple on it, well, the pineapple contains an enzyme, and the enzyme is breaking down the protein in the meat and making it taste more tender. Then again, it depends, of course, on how you cook it, because these structures break down at different temperatures. These thick filaments will break down at one temperature, and the thin filaments will break down at a different temperature. So the feel of the meat, leaving aside its taste, what it's like to chew, will depend upon how it's cooked, whether you like your steak rare or well done. That will affect how much of these proteins are broken down. Now, of course, it's not just this meat, this muscle part of it. That part is connected together to some extent with collagen, holding it all together as connective tissue. So we also have to worry about the collagen. And we've seen that collagen shrinks when you heat it. So when you cook meat, you'd expect something of the sort to happen. Let's have a look at some meat being cooked, Bill. If we could fry up some bacon. Here we have a straightforward rasher of bacon. If we put that into the hot pan and start to cook it, then you'll see immediately that it begins to shrink. You need to tip it up a bit, I think. There we are. That's become all curly and shrunken. That's the collagen, as it gets hot, getting shorter and pulling the meat into a funny shape. So that there you have a problem. When your Sunday joint looks a bit smaller when it's cooked than it did when it was bought, you needn't necessarily always blame the butcher. It's partly that the collagen is shrinking and pulling the meat together into a smaller volume. Suppose we want to make up something like meat. There are various other places from which you can get protein, plants, for example, or eggs. The white of egg is mostly protein. Suppose we wanted to make up some protein that would be like meat. Well, we have to worry not only about the taste of it, and that can be looked after by having various flavoring materials. We need to worry about the texture, because, as I've been saying, it's the way in which it's all put together that gives the impression in your mouth when you're chewing it. So if you want to make artificial meat, we need to make something with the same texture. So let's see if we can make some long chains out of hen egg white. Now, wait a minute. Bill has got some hen egg white in this hypodermic syringe, and he's going to see if he can make some long chains out of it. There you are. If you look into the beaker, you see that long chains are being made. That's something that rather clever cooks do with white of egg when they stir the white of egg into hot soup, and you get long traces of long chains of protein in there. And of course, it's something that people in the food industry are extremely interested in. Over here, we have a vessel which has some protein fibers which have been made up by Unilever research, which are made out of protein, which has been drawn out to make long, thin protein fibers, which you see here. They look rather dry and unpleasant perhaps there, but that's made out of, I think, plant protein. How do we make that seem like meat? Well, we need somehow to organize the fibers into something which has the same texture as meat. And over here we have a way in which that can be done. If you look at this, which looks a little bit like turkey breast, if we look at it closely, say in this direction, you can see there, lined up one against the next, if I point in there, there are fibers running in that direction. And if we look at the end of it, like that, this looks the way meat does when you carve it across the grain. The ends of the fibers are coming out towards you that way. So these fibers like these artificial fibers, have been put together here, assembled here, so as to imitate the way in which protein fibers are assembled in meat. Now, all this talk of food is getting to make me feel rather like food. So let's have a look at this chicken. Here we are now. Let's have a look at that chicken first. You see that's a splendid piece of chicken breast over here, and it's all been roasted for Christmas. Let's see whether Bill can carve that. And he'll carve that rather across the grain, because that's a good way to cut it, because it cuts the collagen into smaller pieces, and that makes them easier to chew. So if we have a slice or two of that, you see that that's nicely cut as a piece of chicken. The only thing about it is that it's actually an artificial piece of chicken. But this is artificial chicken meat assembled on a chicken carcass, and I think, for all you knew, it's even got some stuffing in it down there. That would be a genuine chicken. And I think that that illustrates that if you know what the structure of muscle is like, and you can get protein to assemble in the same sort of way, and you happen to have the right sort of flavoring materials in order to give it the right sort of chicken taste, then you can, by using all this knowledge, put the protein together to give the texture of chicken. You have the taste, and who knows, the food industry soon will be able to create Christmas dinners for us without the intervention of turkeys at all.